Hi everyone. I'm glad to introduce our research GaIA, Graphical Information Gain-Based Attention Network. Different from existing studies, this study aims to reduce the epistemic uncertainty measured by the entropy for a precise semantic segmentation. If two networks show a similar result, it is hard to determine which network is semantically well embedded. To observe whether there is a difference in the estimation of the two networks, Shannon entropy was employed for epistemic uncertainty quantification. In measuring the entropy of each point, it was observed that the reliability of the network prediction may differ even if the same result is obtained. Starting from this experimental result, the question was raised as to whether alleviating epistemic uncertainty improves segmentation performance. To address epistemic uncertainty reduction, we introduced two approaches: reducing the entropy of each point, and effective optimization for points containing high entropy. To identify reliable information, graphical information gain measures the relative entropy between the entropy of the target point and that of its neighbors. It is theoretically based on information uncertainty. The entropy represents the information uncertainty using the probability of event. That is, if the probability distribution of the classes is sparse, a network can make a reliable decision for class prediction. Focusing on this property, entropy is utilized through three phases to alleviate epistemic uncertainty. First, measure entropy of each point. Second, compute graphical information gain. Finally, update the point embeddings with reliable representations. Here, red points indicate relatively reliable points including low entropy. By addressing the limitation of conventional softmax cross-entropy and arc phase losses, ArcPoint is designed to effectively embed unlabeled points. Figure A and B illustrate the original embedding process of arc phase. It embeds the intra-class anchor points similarly while discriminating the inter-class point. Following both A and B, the angles between the unlabeled points and anchors are measured, including different classes. Subsequently, in Figure D, the nearest anchor of each unlabeled point is determined by the smallest angle. Then, the unlabeled point embedding is relocated toward the class which is the same as the nearest anchor. Compared to the existing weakly supervised methods, GaIA improved MAU by 4.4 to 9.4% under the limited annotation benchmark. As shown in figure, GaIA was effective in epistemic uncertainty reduction compared to the baseline. In columns 1 to 3, when both networks exhibited similar segmentation results, GaIA estimated the point cloud with higher reliability at rows 4 and 5. Both figures validate the effectiveness of ArcPoint loss. In figure, dark-colored vertical lines indicate that the unlabeled points have low Cassini similarity compared to other anchors. Moreover, the angle distribution of the baseline network using softmax commonly exhibited a long-tail distribution. This is because the softmax could not enhance both intra-class density and inter-class distinction. We aim to reduce epistemic uncertainty by using the entropy of each point, and it premises that the lower entropy of the network, the more precise the semantic segmentation result is. However, although the network contains low epistemic uncertainty, it can still estimate incorrectly. Hence, the entropy distribution was examined for each class and the distributions of true and false predictions were compared. In both figure, GaIA alleviated the number of false predictions with low entropy. In other words, GaIA resulted in the reduction of false prediction with high reliability. Thanks for listening.